A Universe from Nothing. Why There Is Something Rather Than Nothing by Lawrence M. Krauss.
Mm-hmm. And right out of the gate, I think we need to clarify something about this work.
Yeah, good point. So Richard Dawkins is the afterword contributor here. He's
Correct.
not the co-writer, just to get that completely accurate.
Exactly. It's an important distinction to start us off.
So the whole intention of our deep dive today is to really investigate what modern cosmology can genuinely say about the origin of the universe.
Yeah.
And crucially, what physicists actually mean when they throw around the word nothing. Because it's rarely what the average person is picturing in their head.
Right, which leads to this really specific central question for us. How can modern cosmology explain the origin of a universe containing matter, energy, space, and time from a physical state that may appear to contain almost nothing?
Which is just a massive question. And to even approach an answer, we've got a pretty huge journey mapped out for this conversation.
We do.
We're going to start by tracing cosmic expansion and, how we actually measure those insane distances.
Right, getting into the geometry and flatness of it all.
Exactly. And from there, looking at the cosmic microwave background and primordial nucleosynthesis.
Which then sort of forces us to talk about dark matter and how structures actually form.
Yeah. And then the really weird stuff like accelerating expansion, dark energy, the cosmological constant.
Which drags us all the way down into quantum fields and vacuum states.
Right. And how all that plays with conservation laws and the universe's total energy.
Yeah.
And then we'll hit inflation and reheating, plus some quantum cosmology proposals, the whole fine-tuning problem, eternal inflation, and entropic reasoning.
There's a lot of ground to cover. We're even going to project forward to the future of an accelerating universe and tackle some of the, philosophical objections.
Yeah, and we'll ground all of this in some modern evidence, too. Updates on the Planck mission, Higgs research, the DSI survey, and that whole ongoing Hubble tension debate.
Right.
So let's start with nothing. Like, if I walk into a totally empty, unfurnished room, I'd say, hey, there's nothing in here. But physicists mean something completely different. It feels like people are constantly talking past each other on this.
They absolutely are.
Yeah.
We really need to distinguish between basically 5 distinct tiers of nothingness.
Okay, 5 tiers.
Yeah. So that first tier is just empty, ordinary space, like your unfurnished room, but let's say it's in a vacuum.
Okay.
It doesn't have bulk matter, but it's still full of radiation, light, passing particles.
It's not really empty.
Right. So the second tier goes a step further. It's the total absence of particles.
Okay.
You shield a region of space so completely that no stray electron or photon can even get inside.
But I'm guessing a physicist still wouldn't call that truly empty.
No, because then you hit the third tier, which is a quantum vacuum.
Oh, right.
Even if you manage to clear out every single particle, the underlying quantum fields are still there.
So there's still stuff.
Yes. A quantum vacuum is this boiling, dynamically rich state. It has mathematical rules and measurable properties.
Okay, so what's the fourth tier then?
The fourth tier is the absence of classical spacetime itself.
Wait, how do you even picture the absence of space? Like, where do you put an absence of space?
You really can't visualize it physically. It's something that can only be described mathematically.
Wow.
Usually as a boundary condition or like a quantum state before the actual geometry of spacetime crystallizes.
That is wild. And there's a fifth tier?
Yeah, the fifth tier is philosophical nothingness.
Okay.
This is the absolute void. No entities, no properties, no possibilities, no quantum fields, no math, no logic, just total non-being.
Okay, and we really need to be rigorous here, right?
Yeah.
Because science has never actually observed philosophical nothingness.
Exactly.
Like the entire cosmological argument we're digging into today relies on mechanisms that start from that third or fourth tier.
Right.
Like a physical vacuum or a quantum state.
Right. Science works with observable reality and mathematical models. So moving from empirical forms of emptiness to models of cosmic origins, requires incredible care. We are attempting to describe how physical systems behave, not trying to answer why the concept of being exists instead of non-being.
Right. So since we aren't starting from this philosophical void, let's look at the physical universe we do have.
Okay.
We know it's expanding, but I gotta say, I always struggle with the classic balloon analogy.
Yeah, it confuses a lot of people.
Because space isn't expanding like, debris flying outward from an explosion into some pre-existing empty room.
No, not at all. General relativity completely reframes this. Space itself is the thing that's stretching.
Okay.
The distances between unbound galaxies are physically growing over time. It's like the room itself is getting larger.
But how do we actually know that for sure? I mean, I can't just stretch a giant tape measure out to a galaxy a billion light years away.
Right, which is why we rely on standard candles.
Standard candles.
Yeah, they're astronomical objects whose intrinsic brightness we understand perfectly. Specifically, we use things like Cepheid variables and Type Ia supernovae.
Oh, type Ia, right.
Yeah, a Type Ia supernova happens when a white dwarf star slowly accretes matter from a companion star.
Yeah, okay.
And it will only explode when it hits this very specific rigid mass threshold.
Ah, so because they all detonated at the exact same mass.
Exactly. Their peak luminosity, their true intrinsic brightness is incredibly uniform.
Okay, so it's kind of like knowing exactly how bright a 100-watt light bulb is.
Mm-hmm.
If we see one 10 miles away, we just measure how dim it appears to us, and we can calculate the exact distance.
That's the exact principle. We measure their apparent dimness to get the distance, and then we measure the redshift of their light to see how fast they're moving away from us.
Oh, I see.
And when you plot those two things together, it creates an observational expansion relation.
Okay, so once we have this massive map of expanding space, we can test its geometry.
Yes.
And we always hear that the universe has a near-flat geometry. But I want to make sure we clarify this. We aren't saying the universe is shaped like a giant piece of cosmic paper.
You know, flatness in cosmology is about how parallel lines and angles behave over vast distances. Right. So if you draw a massive triangle connecting three distant galaxy clusters, you can measure the internal angles.
Okay.
In a quote-unquote flat universe, those angles add up to exactly 180 degrees, just like they do on a flat sheet of paper in high school geometry.
Right.
But if space were positively curved, like a sphere, they'd add up to more than 180.
And if it was negatively curved like a saddle or something, it'd be less than 180.
Exactly. And our measurements of the observable universe show that light paths travel in straight lines, and those cosmic angles add up to 180 degrees.
Which is huge. It doesn't mean the universe is infinitely large, necessarily, but it points to a very specific set of initial conditions in the early universe.
Right, which perfectly sets up the conditions for inflation, which we'll get to.
Yeah. But first, what actually fills this flat, expanding space?
Yeah.
One of these incredible baby pictures of the universe, right? The cosmic microwave background.
So CMB, yeah.
But what is that actually showing us? What mechanism captured that image?
Well, it's important to know the CMB is not a photograph of the initial moment of the Big Bang.
Okay.
It's actually a thermal afterglow from roughly 380,000 years later.
Oh, wow. Okay, so quite a bit later.
Right. In the earliest stages, the universe was just incredibly dense and incredibly hot. It was this plasma of charged particles, protons and electrons and photons.
Photons being light.
Yes, but those photons couldn't travel anywhere. Every time a piece of light tried to move, it would immediately crash into a free electron and scatter.
So it was just this opaque, glowing fog.
Exactly.
So how did the fog finally clear?
Well, the expansion cooled the plasma, and when the temperature dropped low enough, those highly energetic free electrons finally slowed down.
And they got captured by the protons.
Yes, to form the very first neutral hydrogen atoms. We call this period recombination.
Yep.
And with the electrons suddenly bound up in atoms, the photons finally had nothing to crash into. The fog lifted.
That is so cool. So that ancient light decoupled from matter and just started traveling freely through space.
Right, and over billions of years of expansion, that light stretched out and cooled into the microwave frequencies that we detect today.
Man, that is just an incredible piece of forensic evidence.
Yeah.
And it perfectly aligns with another mechanism, which is primordial nucleosynthesis.
Mm-hmm.
This part just blows my mind.
Yeah.
In the first few minutes of the universe, before it even cooled enough to make atoms, the actual nuclei of the elements were being forged.
Yeah, the universe was essentially acting like the core of a star.
Right, just smashing protons and neutrons together to build hydrogen, helium, and a tiny bit of lithium.
Yeah.
And when we look at the oldest clouds of gas in the universe today, the ratio of hydrogen to helium perfectly matches what the math says should have been cooked up in those first few minutes.
It does. It completely and independently corroborates the hot early universe model. We have the thermal footprint from the CMB and the chemical footprint from nucleosynthesis.
But of course, as we try to inventory all this matter, we run into a really severe deficit.
Oh, yeah. Big time.
If you add up all the hydrogen, helium, stars, and galaxies, it isn't nearly enough to account for the gravitational behavior we actually observe.
Right. Most of the gravitating matter isn't ordinary luminous matter.
You're talking about weighing galaxies based on how fast they spin,
Yeah.
right? Like there just isn't enough visible mass to keep the outer stars from flying off into deep space.
Exactly. So we infer the existence of dark matter based on that dynamic behavior, as well as gravitational lensing, where unseen mass bends the light of background galaxies,
Oh, right.
and the overarching structure of the cosmic web.
So we know it's there.
Right. And this is a crucial distinction. Successful cosmology can infer unseen components based on overwhelming gravitational evidence without claiming to know their exact microscopic nature.
So we don't know the exact particle identity of dark matter yet, but the gravitational footprint is undeniable. Okay, so we've accounted for ordinary matter, and we have dark matter holding the galaxies together. But the biggest chunk of the universe's inventory is actually driving things apart.
Yeah.
Which is a huge shock, right? Because we expected the gravitational pull of all that matter to eventually slow the universe's expansion down.
But instead, the expansion is accelerating.
Which is driven by dark energy.
Yes,
Huh.
often modeled using Einstein's cosmological constant. The concept here is that empty space itself has an inherent intrinsic energy density. So as space expands, you get more space, and therefore you get more dark energy, which pushes the expansion even faster. It's a runaway effect.
Which perfectly proves your point from earlier about the third tier of nothingness.
Yeah.
Empty space is incredibly active.
Oh, absolutely.
But wait, I want to pause here, because I really want to rigorously challenge this major popular science trope.
Okay, let's hear it.
I read articles all the time that claim quantum fluctuations mean ordinary particles magically appear out of nowhere.
Ah.
Like the idea is that they temporarily violate the conservation of energy, borrow energy from the universe, pop into existence, and then annihilate.
Right.
It sounds like a magic trick where a whole universe can just pop out of an empty hat.
Yeah, we definitely must correct that misconception.
Please do.
The framework we use here is quantum electrodynamics. It describes how light and matter interact. And in this framework, the underlying reality consists of continuous quantum fields, not discrete, billiard ball-like particles.
Oh, okay.
When physicists calculate the interactions of these fields, the math gets unbelievably complex. So to solve the equations, we use tools called Feynman diagrams.
Really?
And those diagrams feature what we call virtual particles.
Okay, so virtual particles are basically just mathematical accounting tools.
Essentially, yes. They are elements of internal calculations representing disturbances in the fields. They are not directly observed, transient objects that are continuously borrowing energy to magically pop in and out of literal existence. The vacuum is a dynamic state of fluctuating fields, but it is not a magical loophole that ignores physical laws.
Okay, but then what about those conservation laws? I mean, in high school physics, we all learned that energy cannot be created or destroyed.
Right.
So if the universe came from a microscopic quantum state, where did all the energy of 100 billion galaxies come from?
Well, local stress energy conservation is firmly established in general relativity. If you perform an experiment in a lab, energy is meticulously conserved.
Right.
However, in cosmology, we often introduce the quote-unquote free lunch heuristic.
Oh, right. The idea that the total energy of the universe is exactly zero.
Right. The mechanism proposed is that the positive mass energy of all the matter is perfectly balanced by the negative gravitational potential energy of the universe.
Okay, walk me through that.
So if you lift a rock off the ground, you add positive energy to it. But you also increase the negative gravitational tension between the rock and the Earth.
No.
So heuristically, as the universe expanded and created matter, the negative gravitational energy grew to offset it exactly.
So no net energy was actually required to make the universe.
It's a beautifully elegant concept. It shows you don't necessarily need a massive injection of outside energy. But we do have to be really careful here.
Why is that?
Because assigning one exact total energy to the entire expanding universe is technically model-dependent in general relativity.
Oh, I see.
Since space itself is dynamic and expanding, defining a global energy state is incredibly complex.
So the zero-energy universe is a really useful cosmological argument, but it's not a universally established measured fact.
Exactly. It's a model-dependent inference.
Okay, but let's assume that balance holds, right? And a microscopic quantum state can expand without violating conservation laws.
Right.
We still have to get from my microscopic spec to a macroscopic universe.
Right.
How does a tiny fluctuation become a whole galaxy?
Through inflation. Inflation is an origin amplifier. It proposes a brief, unfathomably rapid period of accelerated expansion in the very early universe, just fractions of a second after the beginning.
And it literally stretches out those microscopic quantum fluctuations, freezing them into the macroscopic fabric of space.
Yes.
So those tiny ripples in the fields become the denser pockets of space that will eventually pull in matter and form galaxy clusters.
That's it, exactly. That mechanism explains why the observable universe is so geometrically flat and why the CMB has such a uniform temperature across vast distances that seemingly never even had time to interact.
Because inflation smoothed everything out.
Right. But we must differentiate inflation from the standard hot Big Bang.
Wait, really? They aren't the same thing.
No, inflation actually leaves the universe cold, empty, and expanding rapidly.
Oh, wow. So where does all the hot stuff come from?
A physical process called reheating.
Reheating.
Yeah. The rapid expansion is driven by a hypothesized quantum field, often called the inflaton field. And eventually, in our local region of space, that field rolls down to its lowest energy state. When inflation ends locally, the field oscillates and decays. It transfers its enormous stored energy into the creation of standard model particles and radiation. Reheating is the physical mechanism that actually ignites the hot Big Bang.
That is fascinating. And I know theorists try to push even further back with quantum cosmology, looking at the moment before inflation.
Right. Things like wave function proposals or tunneling models.
Yeah.
These models attempt to apply quantum mathematics to the entirety of the universe. They represent the closest physics gets to, quote, creation from nothing.
Okay.
They propose that the universe could transition from a state lacking classical spacetime into an expanding geometry. But their quote-unquote nothing is still a strictly defined mathematical boundary condition. It still relies on a pre-existing framework of physical laws.
And those laws seem incredibly lucky for us, don't they?
Oh, for sure.
Which brings up fine-tuning and the anthropic principle. I mean, if gravity were slightly stronger, the universe would have collapsed immediately. If the nuclear forces were different, stars couldn't fuse carbon. It feels like a rigged game, like a lottery winner marveling at their odds.
Well, the anthropic principle basically states that we can only observe a universe capable of supporting observers.
Right.
It's a statistical selection effect.
Yeah.
But it does not explain why the physical parameters hold the specific values they do.
Which is where the concept of a multiverse comes in, right? Driven by eternal inflation.
Yes. In models of eternal inflation, the rapid expansion doesn't stop everywhere at once.
Yeah.
It continues forever in the background, but stops in local, quote-unquote, pockets.
Okay.
Each pocket undergoes reheating and becomes its own isolated universe.
Wow.
And if the process of forming these pockets allows physical constants to settle at different values, you get a multiverse with diverse, low-energy physics.
So anthropic reasoning just becomes a numbers game then. If there are infinite universes with infinite variations, obviously, we're just sitting in the one pocket where the constants allow for chemistry and biology.
Yeah, that's the reasoning. However, we do not have direct observational evidence of other universes.
Right.
Eternal inflation provides a possible mechanism, but it does not definitively prove a multiverse. And honestly, it merely pushes the philosophical question back a step.
Because it doesn't explain why the overarching meta laws governing the eternal inflationary background exist in the first place.
Exactly.
Okay, so if the background is eternal, what does that actually mean for our specific pocket? We know expansion is accelerating due to dark energy. What's the end game here?
Well, if dark energy remains a constant repulsive force, the expansion will continue indefinitely.
Which leads to a wildly bleak future.
Very bleak.
Eventually, the space between galaxy clusters will expand faster than the speed of light.
Right.
Distant galaxies will simply cross our observable horizon and totally vanish. So billions of years from now, future astronomers on a planet in our galaxy will look up and see nothing but the Milky Way.
Yeah. And the CMB will be stretched far beyond detection.
So all the evidence of the Big Bang will be gone.
Gone. They will formulate a perfectly rational empirical model of a static island universe, and they will be completely wrong.
That is a profound realization. It demonstrates that observational knowledge is entirely historically situated. We just happen to live in a cosmic era where the thermal and chemical footprints of our origins are actually still visible.
We're very lucky in that regard.
But, our observational knowledge is constantly updating, even in our own era. Lawrence M. Krauss wrote the book in 2012, and we really have to separate the book era scientific picture from the massive results we've gathered since then.
Absolutely.
We can't retroactively credit the book with today's science.
No, the field has evolved dramatically. For example, the final data releases from the Planck satellite in 2018 vastly strengthened the precision of the lambda CDM model.
Which is our standard model of cosmology parameterized by dark energy and cold dark matter.
Right, and then you have the confirmation of the Higgs boson from 2012 onward, which fundamentally changed how we view empty space.
Because it proved empty space has measurable properties.
Yes. The discovery of the Higgs field proved that the vacuum of our universe possesses an intrinsic, non-zero structure. Empty space interacts with elementary particles to give them mass.
Wow.
It decisively proves that a physical vacuum is a dynamically rich state, not a void.
And we also have the DSI survey, right?
Yeah.
The Dark Energy Spectroscopic Instrument, releasing major findings from 2024 to 2026.
Yes. DSI is mapping the expansion history with just unprecedented 3D detail. And while largely consistent with a cosmological constant, DSI has produced important, though unresolved, indications that the density of dark energy might actually evolve or weaken over time, rather than remaining strictly constant.
Oh, wait, so if dark energy weakens, the bleak future we just discussed might not happen. The universe might not expand forever.
It's a possibility. It's an active area of research. And finally, cosmology is grappling with the Hubble tension.
Right, I've heard of this.
Basically, measurements of the universe's expansion rate derived from the early universe's CMB do not match the measurements derived from standard candles in the local late-stage universe.
Oh, really?
Yeah, the discrepancy is small, but it's statistically significant. It shows cosmology is now a science of extreme precision.
Wow.
This tension may point to unknown systemic errors or entirely new physics beyond our current models.
Man, bringing this massive journey together, we hit the boundary where physics ends and philosophy begins. Because even if we trace everything back to a quantum vacuum, physics doesn't answer why the state space or the math exists at all.
Right. To synthesize what we have covered today, modern physics successfully explains how a highly simple early state evolved into the complex universe we inhabit. The observational evidence firmly establishes the reality of a hot early universe, cosmic expansion, and the dominant influence of dark sector components. We understand the mechanisms of recombination, nucleosynthesis, and even the theoretical frameworks of inflation and reheating.
But the absolute beginning is still obscured.
Exactly. What remains unresolved is a complete theory of quantum gravity, the exact initial conditions of the cosmos, and the philosophical leap to absolute non-being. Science does not claim to have observed a universe emerging from philosophical nothingness. It has supplied credible mechanisms demonstrating that physical emptiness is dynamically rich, but the transition from a physical vacuum to true nothing remains conceptually open.
This deep dive is an independent COSMORA HQ book overview in audio podcast format. It is not an audiobook, narration, adaptation, abridgment, reconstruction, authorized production, or substitute for the original work. We've been discussing a universe from nothing. Why There Is Something Rather Than Nothing by Lawrence M. Krauss. We strongly encourage all listeners to legally access the original book to engage with the complete argument. We invite your questions and thoughts on this subject. Does modern physics truly explain why something exists, or does it only reveal that physical nothing was never completely empty?